often we have seen that till now we have seen Fourier transforms, and most often we'll find that our function is periodic, and we developed a generalization for an aperiodic function. That is, we tried to write this Fourier transform for Fourier series. For example, I just wanted to convey. So what are Fourier transforms? We have done it. What are Fourier transforms? So we have done it already, but I'm just trying to revise it. Fourier transforms are generally they come into the family of something called as integral transforms. They come into family of integral transforms. Okay, so Fourier transforms are you can say a subset of the bigger family called as the integral transforms. Okay, this is one. The second thing that I want to mention is that in general we'll often come across such functions like integral transforms, you can say, or integral equations. Generally, let's say in physics, you'll find such sort of integral equations, you can say right now. Integral equations, like for example, g of alpha is equal to integral from a to b, and you have this f of x, and you have this k alpha comma t dt, where alpha is a parameter. So quite often in your physics curriculum, you will find such equations. These are called as, in general, you can take them as your integral transforms, or you can say them as your integral equations. Here k is called as a kernel of the integral transform. K is called as the kernel of the integral transform. K is called as the kernel of the integral transform. Let me just write kernel means this is called as your kernel of integral transforms. And till now we have done two of these transforms. One of them is called as your Laplace transform. Another one is called as Fourier transform. The major motivation behind them is, what is the major motivation? The motivation is that at times it may happen that function, for example, to solve an equation in ft. So solving an equation, let's say that is ft, in t space is difficult. So what happens is you transform this ft into some other space. Okay, so a new space. So I transform this ft into a new space. Okay, let's say for here I'm saying alpha space, and from here I can revert back to my original space and get back the solution using the inverse of this. So this particular process of transformation is called as integral transformation. So by integral transformation, I can move from one space to another. And you've seen in your even Laplace transform also that, let's say, I've solved a differential equation. I have solved differential equations using Laplace transform, in which I have shown that differential equations, if they are not solvable in their original space, what do? We take a Laplace transform of that particular differential equation, which reduces them into a polynomial sort of function, and from there we can find an inverse of Laplace transform. Then you can find the solution. So this is one of the good ways, one of the very efficient ways to find the solution of the original equation. This particular part is called as the kernel. So for example, if you are talking about Fourier integral, these a is given by minus infinity, b is nothing but is equal to infinity, and e ki power iota alpha t is your, or e ki power minus iota alpha t, whichever which suits you, is the kernel of a Fourier transform. Similarly, if I take a is equal to 0 and b is equal to infinity, and this k alpha comma t is e ki power minus st or alpha t, whatever, this is something called as your Laplace transform. So in general, remember that both Laplace transforms and Fourier integral transforms, there are many other transforms, like for example Mellin transform, for example Hankel transform. But right now I'm going to discuss in this particular session. One of them I have already discussed, is the Laplace transform. A few classes are left there as well, and a Fourier transform. So we are interested in two of them right now. So one of them is Fourier transform, one of them is Laplace transform that we've already done to a quite extent, and second is the Fourier transform. So understand that Fourier transform, the integral, in Fourier transform, what happens is that the kernel of kernel of Fourier transform is a sort of e to the power iota alpha t. And generally, what does it represent? It represents a plane wave. It represents a plane wave. Okay, so whenever it comes to the study of extraction of knowledge from signals, from waves, study of extraction of function from extraction of information from, let's say, signals, or let's say what are signals. Basically signals have some sort of waveform only, no? From signals and such fields, you'll find that Fourier transforms become an original choice. Transforms are the natural choice. And you know that how these transforms, we've already done it. So basically what happens is that I'll let you know. So what happens is that I know that my function, if my function f, so if my function f is periodic and f dash, they are piecewise continuous function. If they are piecewise continuous function, then they can be written, and they can be written in the discrete basis or orthonormal function, discrete basis of orthonormal functions. And these are what should I say? I mean, these form something called as a Fourier series. Okay, and the natural question that we've been discussing in the last few lectures is that what happens if there is an aperiodic function. So for an aperiodic function, you have demonstrated that an aperiodic function can be written as an aperiodic function can be written as the limiting case, can be written as the limiting case of periodic function. That is, let's say if the fundamental period of this particular function is t, then the limit t tends to infinity of this particular periodic function will certainly lead to an aperiodic function. So basically, what is an aperiodic function? Aperiodic function is you can say that aperiodic function, you can consider it as an limiting case of the periodic function. So basically, if this happens, the Fourier series in the discrete basis for the periodic function reduces to a Fourier integral. So basically, here it is a series in the discrete basis. Here it becomes a Fourier integral in continuous basis. So this is something that we have already discussed. Okay. Now today we are going to start with a few questions, and let's say how to proceed about them. Okay, how to go about them. So we've already discussed a few applications. Okay, let me write down the pairs of the Fourier transforms that we've already done. So pair, and why do I always say pair? Because one does not know what is first original Fourier transform and another inverse Fourier transform. So one needs to write a pair of Fourier transforms. Pair of Fourier transforms. So one has to write pair of Fourier transforms, and here I can write it as f tilde k is simply 1 upon root over 2 pi. 1 upon root over 2 pi from minus infinite to plus infinite. From minus infinite to plus infinite, f of x, and you can write it as e to the power minus iota kx. Oh, sorry, I'm not writing it. Minus infinite to plus infinite, I can write f of x, and I can write e to the power minus iota kx dx. For example, some book says that this is plus, don't worry about it. Okay, Basically I'm writing a pair only. Okay, so this will be 1 upon root over 2 pi from minus infinite to plus infinite f tilde k, and at times this f tilde k is also given written as gk. Yeah, so just see you just make yourself accustomed with these kind of symbols. Okay, so these are the pair of Fourier transform. Each one of them are called as the Fourier transform of each one of each other. Another thing that one needs to pay attention to, that here the function should be piecewise continuous. Piecewise continuous, and the function should be absolutely integrable. The function should be absolutely integrable. These are the two you can say necessities before we can proceed on to finding the Fourier transform of a function. Okay, uh, let us recap of what we are doing actually. Two of the things that one of the very important result that I told you with regards to your examination is the Fourier integral representation of Dirac delta function. This is extremely important for you. Okay, when it comes to examination, this is extremely important result. So what is the Fourier integral representation? Sorry, Fourier integral representation of Dirac delta function. So what is the Fourier integral representation of Dirac delta function? Let's see. So just give me a minute. Okay, so for it, what is the Fourier integral representation of Dirac delta function? Here I'm writing. So basically, I wrote on the very first day, on the previous day. Sorry, this is what you. So I'll write it. So Dirac of x minus x dash is nothing but it is equals to minus infinite to plus infinite. Then I can write 1 over 2 pi as a sort of constant here, and then you have e to the power iota x minus of x dash, and then I will write simply k, and this is dk. So this is how you can represent your Dirac delta function. So basically Dirac delta function which has a very infinitely large peak at x equal to x dash. This is at x equal to x dash. This is Dirac delta function. Okay, now you see this particular Dirac delta function in form of an integral can be written in this way. So basically you can say that this is an integral representation of Dirac delta function. This is an integral representation of a Dirac delta function. One has to remember this. Okay, now let us do a few questions which were asked in your previous year paper as well. So I'll just today my motive is to go with the previous year papers, so that previous year questions, so that you should be able to understand what I'm trying to do. Okay, so today's topic, basically what we are dealing is mostly I'm going to teach you previous year questions. Okay, so that everything gets revised also, and you feel confident. Okay, so this is a question which was asked in net exam of 2014. So this was asked in net exam of 2014, and this says that the graph of the function is given by this. So basically a graph of a periodic function, a real periodic function. The graph of a real periodic function looks this way. So graph of a real periodic function looks this way. Okay. Okay, so graph of a real periodic function looks this way. One wants to find how would the graph of real part of Fourier transform look like? How would the graph of real part of its Fourier transform look like? Real okay, so one has to see uh, although I have taught this you in this previous class. So what, for simplicity, I can take this particular graph as simply let's say this is a graph of, from the figure it is clear that f of x is some cos ax, or for simplicity I'll just take cos of x. It is just cos of x. Okay, you can see, you can write it as cos of 2x also, because no such thing is going to be. We are just making a tentative sort of graph. Okay, we are just making a tentative sort of graph. Okay, we are just making a tentative graph. So just give me a minute. What's happening? I don't know. Okay, so we are making a tentative graph. Okay, so I know this is cos of x. I have to find the Fourier transform of cos of x. So what would be the Fourier transform of cos of x? I can write the Fourier transform of cos of x. I can write it as e ki power iota x plus e ki power minus iota x divided by 2. Okay, this is one thing. And then you see, okay, and okay, okay. So what is Fourier transform? So minus infinite to plus infinite, I will write here e ki power iota minus iota kx into e ki power iota x plus e ki power minus iota x divided by 2, and then dx. So this is the Fourier transform of your cos function. Okay, and what you'll get out of this, you'll get minus infinite to plus infinite e ki power 1 minus of k iota and then x plus e ki power minus k plus 1 iota x dx. Okay, and I have already told you that Dirac delta function is a, you can written, it can be written in form of a integral form. So this is like this, e ki power iota x minus x dash dx dash. And also remember that this Dirac delta function is a symmetric function. So whether you write x dash minus x, or you write x minus x dash minus x, or you write x minus x dash, they're one and the same thing, because Dirac delta function is a symmetric function. This I have discussed in my lectures on Dirac delta function. Since Dirac delta function is symmetric, so therefore whether you write Dirac of x minus x dash or write Dirac of x dash minus x, they're one the same thing. So basically this will be like, first one will be Dirac of 1 minus k, and there would be obviously, so I have not written 1 upon 2 pi, so I'll write 1 upon 2 pi. No, I have not written 1 upon 2 as well, so 1 upon 2 I'll write, and so I'll multiply with pi and I'll divide by. So this is what I'm going to do. So basically this is pi times Dirac of 1 plus 1 minus pi and Dirac of 1 plus k, and there is a negative also. Okay, and since I've written that this is equal to Dirac of x minus x dash is equal to Dirac of x dash minus x, so this is pi times Dirac of k minus 1 plus Dirac of k plus 1. So basically, if this is the graph, that is it, the graph corresponds to somewhat like cosine of x, then its Fourier transform would be some linear combination of two Dirac functions. Right now they are placed at plus 1 and minus 1, so I'm just making a graph here. So this was your cosine of x. Okay, now this particular graph transforms into this particular graph after the Fourier transform. So if I take a Fourier transform for this particular function, this will be like, there will be two peaks. One peak will be appearing at x equal to minus 1, and another peak again will be appearing at x equal to plus 1. So this is how your you can take your Fourier transform would behave like. So this is how your Fourier transform would behave like. Okay, I hope it is clear. So whoever is not getting it, kindly let me know in the comment section. But this is how your graph would look like. I'm waiting for a minute. If there is any doubt, please let me know. Okay, so I don't think there is a doubt here. So I'll move on and see another question. Okay, see another question. Okay, another question, another topic that I taught you in the previous lecture was about. I'm again going to revise it so that the students who have not attended it will find it useful. So another important topic is Fourier transform and contour integrals. So for example, if I want, this is something that I've already done, but still I'm revising it so that you people don't uh, if somebody has not understood it, so that he gets to understand this. So see, what I want to suggest is, uh, let's say I'm discussing about a function. Let's say fx equal to e to power minus of modulus of x. Okay, and how to write the Fourier transform first? Basically, what will happen is, if I want to write the Fourier transform of this particular function, what will happen? So this will be like e to power minus infinity plus infinity. This will be e to power minus of modulus of x, and I will write e to power iota kx dx. This is how you're going to write the Fourier transform of this particular function. So Fourier transform of this particular function, you're going to write it as e to power minus of mod x, e to power minus iota kx dx. Okay, and let's say I'll have to distribute it to two parts, that is from minus infinity to 0. This will be one part. So this from minus infinity to 0, I know that my modulus of x would behave as minus x. So this will be like 1 minus iota k, and there would be x here. And then from 0 to infinity, I know that modulus of x is simply x. So I'll simply write x here. So this is minus 1 plus iota k x dx. So I hope this is clear. Now you see, sorry, I've taught you on the very first day that the Fourier integral would exist only if this integral is convergent. And you see, if you place the lower limit, so I'm just writing it here. If I place the lower limit, what will happen? I know the integral would be some e to power 1 minus iota k x divided by 1 minus of iota. Okay, this is clear. Now if you see, if you place x tends to minus infinity here, so there is e to power iota k. There is already, you see, there is e to power iota k here. So e to power iota k is obviously a periodic function. You know, I mean, periodic function, they are linear combination of some periodic function. Just give me a minute. I don't want this wrong. Okay, sorry for this network disturbance. Just give me a minute. Okay, sorry for this interruption. Just let me reconnect the system. Okay, so I hope the board is visible to you now. I hope board is visible. Okay, so what we were doing was again just part. Excuse me for this network interruption. Sorry. So actually, I was trying to I was trying to revise what we've done in previous lecture. In previous lecture, we found what is the Fourier transform of e to the power minus mod x, and I'm trying to redo it. Just give me a minute. Okay, just give me a minute. Okay. Okay. So we were doing this. Now you see, if I say that this integration, so for example, what I was trying to explain was, see for example, if I just take the lower limit here, so what would the lower limit look like? Lower limit to this particular function would be, not particular function, the integral would be e to the power minus iota k, and here you will get x, and then you have this 1 minus iota kx. Okay, if I take a lower limit, it is equals to e to the power minus iota kx. Forget about it, because you see, because this particular part is a periodic function and a bounded one. So basically, this is a periodic and a bounded function. So I'll write it as a periodic plus bounded function. Okay, and the remaining part is 1 upon 1 minus iota k. So it's again a constant. Forget about it. There would be some e to the power x, and as I take x tends to minus infinity, this will go towards 0. So 0 into any bounded sort of function which will have a finite bounds. Okay, so overall this particular part will become 0 as x tends to minus infinity, and similarly as x tends to infinity this would become 0. So eventually if I want to write the integral this particular, this will be like this, and if it is integration then it is like 1 upon 1 plus iota k. And what it would look like, it would look like 2 upon 1 plus k square. So one has to remember, this is what I have told you yesterday, that 2 upon 1 plus k square, if one wants to take an inverse Fourier transform, which again is a Fourier transform only, don't worry about it. So it would be proportional to some e to the power minus of modulus of x, or probably here it is equal to, if some different things crop up, then in general always remember this is going to be the case. So for example, if I replace it by e to the power minus ax, come on, so I've told you that if the Fourier transform of a function f of x is simply f tilde k, then Fourier transform of ax is 1 upon a f tilde k upon a. So if I want to write what would be the Fourier transform of, see if I want to write what will be the Fourier transform of e की power minus of a, sorry, a modulus of x, it will be equals to 1 upon a, and f tilde k upon a is simply 2 upon k square plus a square, and then you have an a square here. So I know the Fourier transform of e की power minus a x का modulus is 2 times a divided by k square plus a square. So this is how you write your Fourier transform. This is how you write your Fourier transform. Okay, so this is one thing. Now you see, if I just tell you, this is what I have stated in my previous lecture also. Probably a few people might have not got it, so just I'm revising it for you. So for example, if I say, just try to find me the Fourier transform of 1 upon, let's say, x square plus 1. Let's say for simplicity, I'm just trying to find Fourier transform of 1 upon x square plus 1, and one has to remember that I'm defining you this particular thing. So I'm defining you the Fourier transform integration from minus infinite to plus infinite. I'm saying that Fourier transform is given by f of x e की power iota kx dx. So actually it is equal to finding the Fourier inverse transform basically. So I know that in any case this particular Fourier transform, or you can say the inverse Fourier transform, because after all inverse Fourier transform is also Fourier transform, it will be proportional to e की power minus mod x. One has to remember this. In fact, it is equals to e की power minus mod x here. Okay, now I'm just trying to find the same using some different technique, because see, in examination you tend to forget, you will actually forget this result. Not everything you're going to remember. Okay, so if I'm writing what would be the Fourier transform of e की power Fourier transform of 1 upon x square plus 1, given this is the definition, then what it will be? It will be minus infinite to plus infinite, 1 upon x square plus 1 e की power iota k x dx. Now you see, in complex analysis, you've already studied one thing, that if I have to evaluate a definite integral, or you can say an improper integral, minus infinite to infinite, and you have this kind of function that is e की power iota, some mz is there, mx is there, and it is multiplied by with some function f of x dx, then you replace it by a contour integration e की power iota mz fz dz. This is what we do actually. Okay, we replace it by a contour integration. This contour integration contains two parts. One part is on the semicircle, another part is on the real axis. And basically what happens is this particular part goes to 0, and eventually we are left with this only. So therefore this is something referred to as Jordan lemma. And what happens is, here k is this m is positive. Here this m is positive, and we take a upper half of the plane. We take the upper half of the semicircle for evaluating such integrals. Okay. Now what happens in Fourier transform? So see, for example, here when I'm trying to evaluate the Fourier transform of 1 upon x square minus 1, what happens is, I will multiply this with e की power iota kx. K will belong to any real r. Obviously, it can belong to, it can be positive as well, and it can be negative as well. Here we don't have a restriction. So this will be Fourier transform minus infinite to infinite e की power iota kx. I will write x square plus 1 dx. As I stated, I will replace it by a contour integration, which will be equals to e की power iota kz, and then you have this 1 upon z square plus 1 dz, and I've stated this will be equals to this only. And you know from your theory of calculus of residues that this is equals to 2 pi iota into sum of residues. This is equal to 2 pi iota into sum of residues. Okay, this is one thing that you should understand. Now you see, what I want to convey is, see, what are the, when I'm talking of some residues, I need to find what are the singularities. So singularities are clearly z equals to plus minus iota. And please do remember, here k is given to be K can be positive as well as negative. So if I'm taking K positive, then I have to make a contour on the upper half. This is how I'm going to do. And if I have to take K negative, then I'm going to make a contour on the lower half, and this will be this way. Understand this, okay? So if I have to evaluate on the upper half, what is the singularity which will remain? It will remain iota here. And what is the singularity? It will remain here. It will be minus iota. And you have to move. You have to move. You see, clockwise only. Here you have to move anti-clockwise. Here you have to move clockwise in order to keep these limits same. So that I'm leaving up to you. You will be able to understand. If you write K negative, then it will be from infinity to plus minus infinity. If you're moving from in anti-clockwise direction, if K is negative, then these limits will become from infinity to minus infinity. So again, one negative is additionally required. So basically I have traversed, I will be traversing on the lower half in the clockwise direction. Okay, now you see on the upper half you have this iota, so the integral will be 2 pi iota into sum of residue. Sum of residue will be limit z tends to iota, and you have this e की power iota kz divided by z minus iota into z plus iota, and you have again a z minus iota here. So what will happen? This will get cancelled, and you have a 2 iota here. So eventually you'll find 2 pi into e की power minus k. Okay, this is for all k greater than 0. This is for all k greater than 0. This is for all k greater than 0. Okay, and if you see, if I'm evaluating on the lower half, so this will be equals to limit z tends to minus iota, and here I will write z plus iota into e की power iota kz divided by z minus iota into z plus iota. This gets cancelled, and you will get e की power k. Sorry, and this is 2 pi iota also would be multiplied here, so iota gets cancelled with iota. Oh, sorry, if you replace minus iota here, this is minus iota, this will be like minus 2 iota, so this will be pi, and there will be a negative. There will be a negative as well. Sorry, so what I wanted to convey was this will be, I think this 2 pi would get 2 this will be pi only. Okay, so this is pi only, and if I am writing 2 minus 2, if I am placing minus iota here, this will be minus 2 iota. 2 iota and minus 2 iota would get cancelled. This will be minus of pi, and you are going to get e की power minus of plus of k. And don't forget, this particular thing is traversing clockwise, so clockwise would again give a negative more, so you'll get a pi e की power k. Okay, so now what I want to convey is that the Fourier transform of 1 upon x square plus 1 is equals to what? It is equals to pi e की power k if k is positive, and it is equals to pi e की power minus k if k is, sorry, if k is negative, and if it is equals to pi e की power minus k if k is positive. What does it imply? It implies this is equals to pi e की power of minus of modulus of k. This is pi e की power minus of modulus of k. So basically, again, this is what I wanted to convey, that these constants can come in and can go out. Basically, these are just, you can just take them as your sort of, these are not very important as such. This is what I want to convey. So basically, so Fourier transform 1 upon x square plus 1 is directly proportional to e की power minus mod k. Okay, so this is how you are going to understand. So one has to remember, whenever you are sitting in the examination and it is up to the Fourier transform and you are evaluating a contour integral, please don't forget to take a lower half as well, because here you don't have a restriction over k. Okay, here you don't have a restriction over k, that k is positive. If k is positive, then you take the upper half, and all these reasons are related to the convergence of integral, and one has to refer to Jordan lemma for this. So I'm just giving you a brief idea right now. Okay, now let us go ahead and do a few more questions. Okay, so this was asked in some net exam only, so therefore I have done it. Okay, now I'm going to do another question from net exam only, and this is again a very good question. This was asked. It is a question of both. You can say Dirac delta function, differential equations, and also Fourier transforms. So this is how it is. So I'm going to write this question for you, and let's see. Okay, so function satisfies a function fx satisfies a differential equation d2y upon dx2 minus omega square y is equals to minus of Dirac of x minus a, and the Fourier transform was given to you already. Fourier transform was given to you already. It was from minus infinite to plus infinite. It was dx e की power iota kx, and then you had this into f of x. Okay, this was what was given in the exam only. Now you were supposed to find two things. First thing that you wanted from you in the examination was one wanted to find what is the solution of it, solution of the differential equation, and then also like for example, I know the solution would be obviously f of x only, and another thing that was required in this particular question was what would be the Fourier transform of f of x, what would be the Fourier transform of f of x. So these are this particular question contains two parts. So this particular question contains two parts. How to find this particular solution to this particular problem. Okay, so let us do. See, I've told you in the Dirac delta function lecture only. And if you remember, this corresponds to this particular solution corresponds to the appropriate green function. Basically, this right hand side you can find there's a source term. So I'm not using all those terminologies, the difficult ones. Just I'm going with the very basic thing. So what I'll do in order to obtain the solution for the same, I will integrate this differential equation both sides from a minus epsilon to a plus epsilon. From a minus epsilon to a plus epsilon. And what I will do is this will give you d psi upon dx, and then you will have a minus epsilon to a plus epsilon. And you remember I have told you that if I integrate y dx from a minus epsilon to a plus epsilon in the limit epsilon tends to 0, this will go towards 0 only. Because see, after all, this is like integrating from a to 8, but this Dirac delta function will be certainly something, because see, in Dirac delta function, if there is a peak at a, if I'm integrating from a minus epsilon to a plus epsilon, what it will give me? It will give me the area under the peak. It will give me the area under the peak. And we know that in Dirac delta function, the area under the peak is normalized to unity. So basically, it will give you minus of 1. Okay, because there's a negative here. Okay, so what I have obtained is, I have obtained that y dash a plus epsilon minus y dash a minus epsilon is simply minus of 1. This is something that I have obtained. So understand the point. I have obtained that y dash a plus epsilon minus y dash a minus epsilon is simply minus of 1. Now what would say what is y dash then? Okay, one would say what is y dash then? So just give me a minute. Okay. Now you see so here I'm taking consideration and understand the yx is actually the solution only. So you, whether you write y or whether you write f, they are one and the same thing. Okay, so just I'm writing you, giving you one thing. Just consider this: that for existence of Fourier transform, this limiting value of yx at plus minus infinity should be 0. Okay, so it should be 0. If that is not the case, then your integral would become divergent. Okay, so what I'll do, uh, okay, another thing that one can do is, if I take the case x not equal to a, if I take the case x not equal to a, then this differential equation would reduce to d2y upon dx2 minus omega square x y is equal to 0. Or in other words, I can write that this is equal to c1 e ki power omega x plus c2 e ki power minus omega x. And if I drop these c1 c2s and simply take it as 1 upon root 2 and 1 upon root 2, or whichever way suits you. I mean, I just want to find a tentative solutions for this. Uh, so what I will do, because there is no such initial condition given to me, so for simplicity, for simplicity, what I will do, I will write this y of x as simply e ki power omega x. If x is less than 0, that is, if x tends to minus infinity, then this will disappear. And for x greater than 0, I'll choose a solution e ki power. No, sorry. For x greater than a and x less than a, because a was given to be positive. So I'm writing a was given to be positive because these are some things that I've missed in the question itself. So a is given to be positive. See, if you're not able to follow, see what I wanted to say, that for existence of solution, for existence of this Fourier transform, your limiting value of yx at plus minus infinity should be 0. Now what would happen is, see, now for all x greater than a, it will also include the definition x tending to infinity. If I'm saying x tends to x greater than a, it implies I'm also talking about x tending to infinity. And if e ki power omega x, if I'm taking, then obviously this is going towards infinity only. So I'm not selecting here. I'm only selecting e ki power minus omega x for all x greater than a, and only selecting e ki power omega x for all x less than a. I'm not using some constant terms because it will hardly matter, because in question itself also there was no such a hint given to us, so that we'll be able to, so that we are able to find uh, the constant. So basically, the question itself is kind of it's inspiring us, or it's motivating us to find a tentative solutions to this. So basically, a solution that does not contain some sort of constant in front. So basically, what I'll do, this is one. One has to see, or if you want to write some C1, C2, let me write C1, C2, so that it becomes okay. Let me write C1, C2. So what I'll do, there are two conditions. One condition is, C, this is the differential equation. This is the solution for differential equation. This is a solution of differential equation. So even if the hints are not given, what I'll do, there are two hints implicitly given to us. There are two hints implicitly given to us. There are two hints given implicitly to us, and see, if these two hints help us, then we'll be able to find the C1, C2. One hint that was like this, y dash a plus epsilon minus y dash a minus epsilon should give us minus of 1. And another hint is that yx must be a continuous function, because after all this satisfies a differential equation, so yx must be a continuous function also. So yx must be a continuous function as well. So two things are implicitly given to us in the question itself. Now you see, if I use both of these conditions, so for example, if I use the first condition, so what is a plus epsilon? In a plus epsilon, this is the definition, so I'll get minus omega c2 e to power minus omega a minus at a minus epsilon. This is omega c1 e to power minus. This is one thing. Okay, and it should be continuous. So if it is continuous, then I will write limit x tends to a minus y of x must be equal to limit x tends to a plus y of x. So if I'm writing a minus, that implies for all x less than a, this is c1 e to power omega a minus epsilon is equals to c2 e to power minus omega a plus epsilon. And from here, I can write that my c2 is equals to c1 e to power 2a omega. c2 is equal to c1 times e to power 2a omega. This is very much clear. And if I replace this, this is slightly lengthier question, but what can be done? So if I replace this, I'll get the values. Okay, so if I replace this, I'll get minus omega c2 instead of c2, I'll write c1. This will be e to power omega a minus omega c1 e to power omega a. This is minus 1. So basically what is happening, c1 comes out to be 1 upon 2 omega e to power minus omega. And what would be c2? c2 would be simply 1 upon 2 omega e to power a omega. Okay, so c1, c2s both are found. So basically, initially we were hesitating from writing constants. Even if we write constant, we are getting the value, so don't worry about it. Even if we are, so one has to, so I'll improvise my solution as this. Y of x would be equals to what? Y of x would be equals to what it was given. For all x greater than a, it was, for all x greater than a, it was, I think, just give me a minute so that I just see. For all x greater than, it was c2 e to power minus omega x. c2, so I'll write c2 is this into e to power minus omega x, and here I'll write e to power a minus a omega, and here I'll write e to power omega x. This is for all x. This is x greater than a. This is x less than a. Okay, clear? I hope it is clear. So basically what is happening is your y of x, if I want to write it in a more compact sense, I can write it as 1 upon 2 omega e to power of minus of this a is, omega I can take common out. Omega I'm taking common out, and I can write modulus of x minus a. Y of x I can write it as 1 upon 2 omega e to power minus of omega modulus of x minus a. See why? If I take the case x greater than a, this will be simply x minus a. So it will give me e to power minus of modulus of x into omega a. See, if I am taking x greater than a, this will be equals to 1 upon 2 omega e to power minus of omega x plus omega a. So basically it will be like this only. If I am writing x less than a, then how would it behave? It will be 1 upon 2 omega e to power minus omega. This will be a minus of x then. So it will be this. Okay, so basically this is how you define. So this is what this was what was asked in the examination from us. The first thing that was asked with regards to this differential equation was, if this is given to us, then first thing that we were to find was solution for the differential equation f of x. Basically, if you write y of x, because see, function f of x satisfies this differential equation, means whatever is the solution is f of x. So I found that solution y of x is equal to 1 upon 2 omega e की power minus of a modulus of x minus of omega modulus of x minus of a. I found that f of x. Now I need to find the Fourier transform for this particular f of x. So now the next part would be to find the Fourier transform. So let us find the Fourier transform of this function. I hope everybody has got. If there is certain thing that you're not able to follow, kindly let me know in the comment section, and that I will be so grateful to you. But overall, please understand. Try to focus. I mean, this is an important topic for your examination. So if I want to find the Fourier transform for this particular function, which is very complicated as such, I'll write 1 upon 2 omega. Here you have e की power minus of omega mod of x minus a. Then what it will be? It will be like 1 upon 2 omega integration from minus infinite to plus infinite. You have e की power of iota ki x e की power minus omega modulus of x minus of a, and you have this t of x. So I'll break it in two parts. One part would be from minus infinity to a, other part would be from a to infinity. Okay, one part would be from, so there is 1 upon 2 omega. One part I'm breaking from minus infinity to a. This will be e की power iota kx e की power it will be for all x less than 8 is equal to minus omega x, and then I have omega x dx, and from a to infinity it will be again 1 upon 2 omega. I'll write here e की power iota kx, and then I will write e की power minus omega x into omega a. Okay, so eventually this will turn up that this is 1 upon 2 omega. I'll write e की power omega minus omega a outside, and this will be like e की power iota k plus omega times x divided by iota k plus omega from minus infinity to a. This is one part, and then 1 upon 2 omega I will get e की power iota k minus omega divided by iota k minus omega, and this is like x here, and you have this e की power omega, and this is from a to infinite. You see, if I take x tending to infinite, this minus omega x would take it towards 0. So don't worry about it. So at x equals to plus minus infinities, your here the upper limit would be 0, and here the lower limit would be 0. So I'm not bothering about that, and I'm leaving it to you to understand this thing. Okay, and if you really find some problem in it, let me know. If I'm not placing, if I place a here, this will give me omega a, and here there's omega a. Forget about it. So 1 upon 2 omega e की power iota ka divided by iota k plus omega, and then write this also 1 upon 2 omega. If I use this tending to infinity thing, this will give me 0, and then again I have to place there is a negative sign as well, so there will come a negative sign. This will be e की power iota ka divided by iota k minus omega. So eventually I will find this as e की power iota ka divided by 2 omega, and I will get it as iota k minus omega minus iota k minus omega divided by minus of k square minus of omega square, and eventually I will find that this particular term is equals to e की power iota ka. This will get cancelled, 2 would get cancelled, 2 omega would get cancelled, so you'll get a negative, so you'll get k square plus k square. So this is what is your Fourier transform. So Fourier transform of your function f of x is e to the power iota ka divided by k square plus omega square. I hope each one of these things you've got in your in this particular lecture that I've covered, you've got. Kindly let me know if there's a certain thing that you're not getting, or there is something that I can improve. Overall, I feel that probably the next session would be the last session for Fourier transform, and then we'll begin with some other topic. Okay, till then, take care. Bye bye.